are a few calculations and derivations we're going to do in our notes today on circular motion applications. Okay, so again, please have out some paper. You're going to have to be able to do this on your own later on, and you're going to want to have something to look back at. We're going to start our discussion today with conical pendulums, and this is the portion of the notes that, well, actually all of our notes today are on conical pendulums, but we needed to discuss this in order for you to do the activity, that flying pigs that I was talking about. You have to be able to know how to do calculations with a conical pendulum. Okay, so what is a conical pendulum? It is an object attached to a rope or string so that when it moves in a horizontal circle, the string moves at an angle to the vertical. And I have a picture or an animation up here of what that would look like with an object. This one's like a blue sphere that is attached to this string, and it's moving in uniform circular motion, okay, as it is suspended from the ceiling. Yes, ma'am?
What slide is it?
Yeah, if you want to follow along, I am on slide 70. All right, so again, there is uniform circular motion in a horizontal circle. Thus, if we have uniform circular motion, we know that that means we must have net force and acceleration. Since we're talking about a horizontal circle, that means we're going to have horizontal net force, and our centripetal acceleration will be toward the center of our horizontal circle. And so we're going to be dealing things now in that horizontal direction. Unlike the notes the other day, everything was vertical then, now we're looking horizontally. The ball in this case, or whatever it is that is suspended from the end of your pendulum, does not move vertically. There's no upward or downward motion or acceleration of any kind. There is no vertical acceleration, and therefore vertical forces are balanced. Okay, so you have to keep that in mind as we start looking at the math and the different equations we're going to derive. We need to know that those vertical forces remain balanced whenever we're looking at a conical pendulum. So again, to kind of summarize what's happening here horizontally and vertically. Vertically, again, your pendulum does not move in the vertical direction, therefore your forces are balanced. Horizontally, you have uniform circular motion, and therefore you have a net force that is a centripetal net force that is causing centripetal acceleration. So again, you need to understand those concepts so that we can start to analyze different scenarios. You may also want to sketch out a picture of what your conical pendulum might look like. This is at a point frozen on the left-hand side of that circular path, but again, you could draw this anywhere. But you'll need some of these different terms. Of course, we have the mass of the pendulum bob itself, whatever it is that's attached. We have the radius of that circular path. Labeled here as R, and then we'll use a capital L to label the length of the string or rope or whatever it is that we're dealing with for a pendulum. So you want to be familiar with those variables. You're going to see them again. So if you don't copy it down here, there will be more pictures, I promise. In fact, probably the same one. Okay, so we're going to start by drawing a free body diagram for the object attached to the string. For this, we're going to assume that the system is just the red ball at the end of the string. The string's not part of the system, therefore it can exert an external force, and it can be drawn in our free body diagram. Okay, and so here I have my pendulum bob, the red ball over here, and we're going to draw the forces acting on it. Okay, so when we draw our free body diagram, we want to make sure to draw FG always straight down. Okay, what other force or forces do we need to include? Tension. What direction is it going to be in? I just heard a weird answer. I heard down. No, it will be at an angle, okay? At an angle going up, and based on this position here, up and to the right, okay, is how it should be drawn for the position shown, okay? For the position shown up and to the right. And we're not going to have any other forces to diagram here, okay, because we're going to assume there's no air resistance. Unless the question tells you otherwise, you should always assume that there is no air resistance in that problem. Okay, and so here we're going to have these two forces. Now, Again, we've talked about this previously, but whenever we start to analyze the forces, we need to analyze them whenever we're only dealing with things either that are vertical or horizontal. So if we have a force at an angle, which we do, we will need to get the components of that force in order to analyze, in order to be able to write our equations, like for second law, all of that. You can't deal with it when it's at an angle. Okay, now, so we are going to have to do some trig here. However, please be mindful of which angle is given for your pendulum. It will affect the trig. I'm going to give you the angle in a couple different places, and that of course is going to affect how you solve that problem. So I'm going to label this angle right here as theta. Okay, I've added it to my picture, and so I'm going to talk about things with respect to this angle down here. So I've redrawn my diagram, I've labeled theta on my diagram, and again, I need to get those components of my force of tension because I can't analyze it whenever it's diagonally. So I need to get the horizontal component, which I'm going to label as force of tension in the x direction, and I need to get the vertical component, which I'm going to label as force of tension in the y direction. Okay, and again, whenever we do this, we can write out equations for ftx and fty that relate them back to ft, okay, using trig. Okay, I know that fty I could set equal to ft times sine theta. Again, in the case of this blue vector, my vertical component, I'm using sine because this component is opposite my angle. For my purple component, my x component, ftx, I'm using cosine because this is adjacent to my angle, and so I can say ftx equals ft cosine theta. Okay, now, although on your test you would be drawing a free body diagram that looks like this, you don't draw the components, you draw the actual forces. In order for us to actually start analyzing this problem, we do want to go ahead and redraw it. So if you're trying to do this on a test, redraw it out to the side or somewhere other than the place that they've provided for the answer, unless it tells you that you're allowed to draw components. Okay, so again, typically you're not. So I'm going to redraw it, and I'm going to have my FG, again, that's still there. I'm going to have FT in the X direction, and I'm going to have FT in the Y direction, and those are my components, and therefore I now can look at these forces in a way that allows me to analyze the situation and even do some calculations. Okay, again, I know Fy is equal to Ft sine theta. I know Ftx is equal to Ft cosine theta. And so again, if I had some numbers, I could start trying to figure out how to solve something here. And in order to do that, you're going to start by writing out second law equations. Okay, I know that in the y direction I have balanced forces, and so my second law equation ends up looking like this, where the force of tension in the y direction is equal to the force of gravity because the sum of those forces is 0. Okay, again, my net force vertically has to be balanced, and I know that because when we talked about conical pendulums, we said there is no vertical motion, much less acceleration, therefore we need vertical balanced forces. Okay, and so I can say that Ft sine theta equals F sub g. Whenever I look at, I can substitute in mg here. So now I've got it where I could plug in mass, gravitational field strength, and angle, and my force of tension if I had those numbers. I'd be able to plug any of those in there. Okay, let's look at it in the x direction though. In the x direction, I do have a net force, and so my second law equation here, again, you can write it as F net x equals m times ax, or I've rearranged it and I have my centripetal acceleration in the x direction because it is a centripetal acceleration. We're talking about uniform circular motion in this horizontal plane. Okay, and so I have my centripetal acceleration in the x direction equals F net x over m. I know that my F net x is just the force of tension. It's the only force that I have in the horizontal direction, so I'm going to substitute that into my equation. And now I have my force of tension, the x component of it, divided by mass gives me my acceleration. And again, I can substitute Ft cosine theta because the question's not going to give me a component. It's going to give me the total amount of tension. Okay, so I need to get to a place where I am able to actually use these equations to substitute numbers in or to to use them to derive something else. Okay, so again, this is what you end up with for your second law equations in either of these cases. Before I go any further, does anybody have a question about either of these? Yes, sir.
Why is everything divided by mass for the x?
Because of this equation right here. Again, F net equals M times A. That's the formula. If you rearrange it though, you have A equals F net over M. So you're going to be dividing by mass because that's part of Newton's second law. You have a question?
Like, what's the difference for, like, use A equals B squared over R? Like,
I haven't gotten there yet.
Oh.
We haven't solved a problem. I'm just deriving the second law equations. We could absolutely use that, and we will be using that in a minute.
Okay.
Okay. All right, so again, conical pendulum calculations may ask us to solve for centripetal acceleration, tangential velocity, period, etc. I could ask for any of the variables. So what I have here is really a starting point. Okay, I have second law equations that I can use to find these things. We can use the horizontal equation, this one here, this is the vertical one. We really need the horizontal equations in order to find those things because that acceleration is horizontal, because that net force is horizontal. Most of it's going to be focused on this one over here in purple. However, this one over here with my green arrow you can use if you're trying to find FT because you're probably going to be given information about an angle, a mass, and of course you know G on Earth. Okay, so that equation would be helpful to you if you're trying to determine that force of tension because it obviously shows up in both equations. So you might end up needing both of them even though all of the things you're going to be asked about are pretty much in the horizontal direction. Okay, you still want to have that vertical equation written out. And guys, please don't get focused on sine goes here, cosine goes here. That is not necessarily the case. I told you, make sure you pay attention to where the angle is labeled in that question. Okay, so let's go ahead and see what else we can derive. Obviously, I know my centripetal acceleration is Ft cosine theta over m. And since both of these equations have force of tension in them, I can substitute this force of tension into this equation. And so I can substitute in mg sine theta times cosine theta, all of it over m, equals my centripetal acceleration. So if I was trying to find my centripetal acceleration, I now am a step closer to doing that. Okay, looking at this equation, it looks really complicated, but I can simplify it because I can cancel out those masses. Okay, and when I do that, I can rewrite it like this. So my centripetal acceleration, again in this problem, would be g cosine theta over sine theta. And that's something I probably have the information for. They're going to give me an angle. Okay, I know what g is, and so I could use this formula if I wanted to solve for my centripetal acceleration. But maybe they're not asking for centripetal acceleration. Maybe they're asking for tangential velocity or period or something else. Well, again, that just means you have to take it a step further or 2 steps further or whatever. Okay, which we're going to be doing. Okay, so generally the radius is not given to you. Okay, usually they don't tell you, hey, the radius of this circular path is, 0.7 meters. Instead, they'll tell you the length of the string, okay, or the rope that the pendulum is suspended from, and they'll tell you an angle. Okay, and so because you don't have the radius given to you, or at least you're unlikely to have it, you need to be able to determine what the radius is as well in terms of the things you do know. And so because these are both lengths, radius and length are both measurements of distance, okay, you can write an equation like this. Cosine of the angle theta equals, again, cosine is adjacent over hypotenuse, and these do form a right triangle. You can see it in my picture. And so I can say that it's equal to r over L. And then I can, of course, multiply both sides by L to get that r is equal to L cosine theta. Okay, and so if you don't have the radius but you need it, there's a way to get it, because they're probably going to give you an angle and the length of a string. Note that if the vertical angle is given instead, this equation is going to look different. Same with the last one we derived. I gave you this angle. It is entirely possible that you will be given this angle instead. Okay, so you can't just use the equations we wrote for everything because they're not going to work unless this angle at the bottom is labeled. Okay, so let's look at some more examples because as I said, I'm going to do it both ways. Okay, so this one we're actually going to solve for mathematically as well. So we're going to be deriving some equations, but we're also going to be solving for a number answer at the end. I would copy this down if I were you. It is a very long derivation though. Okay, just a warning. It says a ball on a 3-meter long string is slung in a conical pendulum with an angle of 30 degrees from the vertical. Determine the ball's period. So again, we're going to start by drawing a free body diagram. I know that I want to draw FG every time, and I'm going to draw it straight down. And I know that my pendulum, again, I know whenever I'm dealing with this, I'm going to draw my force of tension at an angle. And in this case, they're telling me the angle from the vertical. This is not the same angle we used a second ago. Okay, and so I have an angle from the vertical labeled instead. Again, I always need to get components. Okay, in order for me to actually solve for anything, I need to figure out how much of my force of tension is in the x direction, how much is in the y direction. And again, you really wouldn't want to draw these on your actual free body diagram on your test, but you could draw it out to the side. Okay, so try it. See if you can write second law equations for the x and y direction. What can you tell me about the y direction? Let's start there. Balanced. Okay, so in the y direction, I know that I have 0 acceleration because I have balanced forces, and that means that I know that Ft in the y direction, my y component, is equal to Fg. Okay, and I know Fg, I'll start with Fty. I know that that's Ft cosine theta here. Again, this is different than the last one because of the way we drew it. My y component is adjacent to my angle, so I have Ft cosine theta equals Fg. And again, I don't want Fg in there. Let's get it to a point where we can substitute in numbers that we might actually have. Okay, Ft cosine theta equals mass times gravitational field strength, little g. Okay, similar process, slightly different looking equation. Okay, what about horizontally? Do I have a net force horizontally? Yes. I only have one force in the horizontal direction, but I have a net force. I have that one force, my Ft in the x direction, causing that acceleration to the inward to my circular path. Okay, and so I'm going to plug in my Ftx, that x component, that is my net force. And so my acceleration in the x direction equals my net force, that Ftx over m. Again, Ftx is Ft sine theta. Okay, again, based on the way I've drawn it, it is opposite my angle, and so I'm using sine for this one. Okay, and so my centripetal acceleration, that x acceleration in the horizontal direction, is Ft sine theta over m. Again, we're ultimately trying to determine the ball's period. Okay, we got to get period in an equation somehow. Okay, so let's see what we can do with this. Okay, what do you think we should do next? Period's not on my screen at all, by the way, and that's okay. We're not going to get there in one step.
What's the probably
Okay, we can do what we did a minute ago in the last equation because there is something common between these two. Okay, or we can go here. Okay, so this is a little different than the way we solved the last one. I know that I have acceleration equals Ft sine theta over m, and I know, and this is the one you asked me about a minute ago, Kat, I know acceleration is also v squared over r. We talked about that in the warm-up. So I can set those equal to each other because they're both equal to the centripetal acceleration. So I have v squared over r equals Ft sine theta over m. And that's helpful because once I get velocity in there, I can get period in there. Okay? So again, I know that I'm looking for period, and I know that tangential velocity is 2 pi r over period. So there's the period I'm trying to get in to my equation. And so I can substitute that in. 2 pi r over t, all of that squared, because that's v, over r equals Ft sine theta over m. Okay? Again, I can't solve for period like this. I got to get some of these variables out of here that I don't know yet. And so that's where you start to look, how can I get rid of some of these things? How can I get Ft out? How can I get m out? How can I get it so I'm at a point where I only have the length of a string and an angle, because those are the only numbers you have. Okay, so I know from the previous slide that I can use my y component. Even though it's not really what I'm solving for, I can use it. Okay, I know that ft is equal to mg over cosine theta, and here's ft right here as well. So let's start, and this is kind of what we did in the last example, but let's start by getting rid of this force of tension and substituting in mg over cosine theta times sine theta over m, and again, here's my v squared over r over here. Okay, and again, this is going to allow me to get rid of the extra radius in here. Okay, I went ahead and squared this whole thing. So 2 pi r over t squared is 4 pi squared r squared over t squared. But again, it's all divided by r, so I canceled out one of those. I can also cancel out the masses. That was one of the things I didn't know. They didn't tell me the mass, but I can cancel it because I have it both on the top and on the bottom. So we have a much simpler looking equation. Still not simple, but simpler. Okay, not as complicated looking. A lot of algebra. All for one calculation. Okay, so it's a long derivation. So now we have 4 pi squared r over t squared equals g sine theta over cosine theta. I'm going to go ahead and move that t squared off the bottom. Ultimately, if I'm trying to solve for period, I don't want it in the denominator. Okay, and we can go ahead and divide both sides by g sine theta and multiply both sides by cosine theta to get that period squared by itself. When we do that, we get this equation. 4 pi squared r times cosine theta over g times sine theta equals period squared. So we're getting closer to the point where we can solve. The question you have to ask yourself is, do we know r, do we know theta, and do we know g? We do know theta and g, but we don't know r. So we are not quite there yet. However, we can figure out the radius based on that equation I showed you a moment ago. Remember, length and radius form a right triangle as well, and so we can use some trig to relate the length and the radius like this. Sine of the angle theta equals opposite over hypotenuse. Again, based on where my angle is drawn, from the vertical this time, opposite is now r, hypotenuse is L. And so it would be sine theta equals r over L, or r equals L sine theta. And now I can substitute this in for r over here. So instead of 4 pi squared r, we can have 4 pi squared L sine theta times cosine theta over g sine theta, all of it under a radical, equals t. We can solve it now because we have all the numbers. Okay, you could simplify it and cancel out the sine theta if you want, because it's on both the top and the bottom. Okay, but if we plug those numbers in, okay, if we go ahead and plug in, it looks like this. 4 pi squared times my length of the string is 3, it's right here, 3 meter long string, times sine of 30 degrees, times cosine of 30 degrees, divided by 10, that's g, times sine of 30 degrees. Again, if you put all that in there, and then take the square root of it, you will get a period of 3.20 seconds. Very lengthy problem. But guys, you'll have to practice derivation. Okay, you have to practice it. Okay, does anybody have a question about this? I tried to color code it so that you could click back through later and see where everything went or came from. Yes, Grayson?
I'm sorry. Something like, where does the period come from?
Period came from, for velocity, is 2 pi r over period.
Okay, velocity is 2 pi. Would this be one of the more difficult questions that we would have to do?
Yes. Yes, Kat. Maybe. Wait, please. Hold on 1 second. All right, guys. So for the rest of the period, okay, you have playlist 2, which is due on the 12th. Your FRQ test corrections due on the 11th. I did, and I put it here, extend the retest deadline, because guys, listen up. The retest deadline was Monday. However, we have a science department meeting on Monday, and therefore none of the science teachers will be available to host tutorials on Monday. And so if you were planning to retest on Monday, I'm sorry, we won't be here. However, we will be here on Tuesday instead. Okay, and so you can stay through Tuesday after school, and then of course your lab binder due date is coming up. Your TEKS test is on Monday. Don't forget you have a review in AP Classroom for the TEKS that you can also use for the final exam. Go ahead and get to work. If you have questions for me, please let me know.